phi in this group. So we are looking for what are the superposition free operators to achieve these transformations, or what are the conditions for deterministic transformations. So before proceeding, let me remind you the coherence transformations. As I mentioned before, coherence is a special kind of superposition, so it can be useful to remember coherence. In the case of coherence transformations, we know that majorization condition, which is proposed by Liu et al. In that paper, the majorization condition is a necessary and sufficient condition. It means if the majorization conditions is satisfied between these two coherence states, then this transformation can be achieved with unit probability. To achieve these transformations, we have some incoherent operators, Kn, and they are given in this form. Here, F and K are some index functions or some permutations or some unitary transformations. All of them is the same. Also, we have some completeness relation. In the case of coherence, a set of cross operators is sufficient. We will see that in the case of superposition, we need another set of superposition-free operators. So if we construct a proper way of obtaining these permutations or unitary transformations, then we can solve these equations and we can find probabilities. If you find probabilities, then we can obtain the cross operators. So in order to obtain these permutations or unitary transformations, in 2018 we proposed a method for deterministic coherence transformations for achieving these transformations. So in this task, in this superposition state transformation task, we also benefit from these results. So if we return to the superposition state transformations, we have some superposition free operators in this form. And this superposition free operators gives target states phi with some probability Pn, which is given in this form. Here, there's a crucial important point. As I mentioned before, the set of class operators Kn gives us the target state with some probability. Also, we need another set of class operators Fm to obtain the completeness relation. Also, here this class operators Fm gives us nothing. So it is necessary only for completeness. Also, one crucial point is that here, in order to have such class superposition free operators Fm, we need to satisfy this inequality. In other words, Kn dagger Kn, some of these operators must be less or equal to identity. This is the most important part of this setting. Okay, so if we find index functions, we can find probabilities. If we find probabilities, we can find cross operators. If we find all of these terms, then we can get some idea about the conditions for deterministic superposition transformations. So what are the results that we obtain? Here, contrary to the coherence, majorization alone is not sufficient condition for superposition transformations. We need another condition, which we call conditional completeness, or abbreviated COC. Here, in this part, there are state transformations here, where only the majorization condition is satisfied, and here only the condition on completeness is satisfied. For deterministic transformations, these two conditions must satisfy at the same time. So what is majorization for superposition? We reformulate majorization for superposition in this form. Here, psi I tilde or phi I tilde are given in this form. They contain overlap between the based states. So it is easy to see here if the basis states have zero overlap, these majorization conditions reduce to the majorization condition for coherence. So this is the majorization for superposition. The second condition, conditional completeness, is given in this form. Here, probability, this pi is the probability of the outcomes. Omega ij are related with the coefficients of the final superposition states. Here also we have a capital Pi. This is the permutations or unitary transformations, and these are related with index functions. So from the completeness relation, we have these equations. If we solve these equations, we can find cross operators. Okay, here I want to give some examples for qubit systems. In the first two examples, in the first one, majorization is satisfied, but the conditional completeness is not. In the second example, this time majorization is not satisfied, but conditional completeness is satisfied. So these two transformations cannot be achieved with unit probability. However, the third one, in the third example, both majorization and the condition on completeness is satisfied. So this transformation can be achieved with unit probability. To achieve these transformations, we have two cross superposition free operators K1 and K2. If we apply this K1 and K2, we can obtain these final states with some probabilities and totally with unit probability. Also, as I mentioned earlier, we have another set of free superposition free operators, which we need to achieve completeness relation. Also, in fact, we don't have to construct explicit form of these cross operators. The only thing we need to have is this one. Ki dagger Ki must be less or equal than identity. If this highlighted in red equation is satisfied, then we know that we can find a second set of superposition free operators. So, for example, here I choose F4 equal to 0, but we do not need to choose this one. We can choose it different from 0. Anyway, this kind of examples can be diversified. If I repeat again, for superposition state transformations, majorization alone is not sufficient. We need another conditions. This is conditional completeness. If this both conditions is satisfied, then the transformation is can be achieved with unit probability. Also, we need to check whether these two conditions reduce to majorization in the orthonormal. What I mean with orthonormal limit, if the overlap is 0, then we can check the orthonormal limit. If we look this limit, then we see that these two conditions reduce only one condition, which is majorization for coherence. Here we have D minus 1 inequality. Also, this inequality holds equality for the orthonormal limit. This D minus 1 inequality actually is same with these equalities. So we do not have new equations. So in the orthonormal limit, we only have majorization condition. Again, here we have some index functions, and our the second set of free operators are all equal to 0. We don't need them anymore. So I also mentioned about the paper written by us in 2018. In that paper, we propose a method to obtain these permutations. For example, consider d equal to 3. We know that from majorization, the first coefficients between initial and target states, this inequality, and the last coefficients between initial and target states, these two are already satisfied from majorization. But the other coefficients, beside 2 and 2, does not have a single relation. It is either this one or this one. So for each one, we have different set of permutations. As I mentioned, how can we obtain these permutations? We propose a method in this paper. So I conclude this part with this explanation. In the second problem, I want to discuss about the states with maximum superposition. We know that in the coherence case, the maximally coherent states are well known and they are given in this form. But in the superposition case, it is more challenging due to the non-orthogonality. So here our aim is to find a way to catch the form of the superposition state, or to find a way to show the existence of superposition, maximum superposition state. So we have a proposition which is based on a Gram matrix. Let's say we have a Gram matrix or overlap matrix whose elements can be obtained the basis states of the superposition, resource theorem of superposition. Then a maximal state psi is necessarily an eigenvector of the overlap matrix corresponding to the minimum eigenvalue lambda min. And here the component of this eigenvector must be 1 over d. Here, please pay attention. We have psi I tilde. So we previously defined this psi I in this form. So this condition also must be satisfied. So this is our first proposition. From this proposition, we have a corollary. Then the form of candidate maximal state dictated by proposition 1 is as follows. Here, this one in the bracket notation. Also, as we mentioned here, these are the candidate states. If they want to be a golden state, this condition beside I tilde also must be 1 over d. This is also another condition. So to prove all these proposition and corollary, we apply Rayleigh quotient. Rayleigh quotient is a mathematical tool to show the minimum and maximum value of an eigenvector of Gram matrix. For example, let V and U be the eigenvector of Gram matrix G, where the first one corresponds to the lambda min and the second one corresponds to lambda max. Then let X be an arbitrary vector under the elliptic constraint, which is given in this form. For example, this is also a normalization condition. Then for these three vectors, we have a Rayleigh condition that guarantees this. So if we apply this Rayleigh quotient to some initial superposition state and to some final superposition states, we also want to this initial state to be maximal superposition state. We obtain this condition. So this is a Actually, this is a necessary condition for being a maximally superposition state. So, proposition 1 is the most general form of our proposition. So we can make it easier with additional proposition. For example, in proposition 2, we consider the case qubit systems. For example, if we have basis states C1 and C2, and then we construct gram matrix, and then if we obtain eigenvalue and eigenvectors of this gram matrix, then we will see that the eigenvector which corresponds to the minimum eigenvalue is a maximal state for superposition. For example, consider here, let's say C1 and C2 equal to their overlap equal to S, which can be in the range -1 and 1. If you obtain these gram matrix eigenvalues, we obtain two eigenvalues. So it is obvious that we have two different situations. For example, lambda mean equal to 1 minus S when S is in the range 0 and 1, and lambda min is equals to 1 plus S when S is in the range -1 and 0. So for qubit systems, we have two golden states, and they are given in this form. Once again, I want to remark that each one corresponding for some particular range of overlap. Okay, so this proposition is for qubit system. We can check these states, whether these states are maximally superposition or not, with some diagrams which we wrote by using L1 norm of superposition. Here, the dashed lines are the maximal states, these states, and the other ones are some arbitrary states. We know that we write any superposition state in this form. We can check we can change this eta, and we'll see whether we can obtain a state which contains more resource or not. This diagram shows that it is not possible. So these states are maximal superposition states for qubit systems. So we can diversify these examples for d equal to 2, d equal to 3. Here we have a table. We have different kind of overlaps between the basis states. As I said, we can diversify all these examples. For example, here, if we consider this case, we will obtain that this state in the range where S in the range 0 and 1 or 2, this state is the maximal superposition state for this choice of overlap. Okay. So last proposition is about the d-dimensional systems. For d-dimensional systems with real inner products, we have a superposition state in this one. So we can look any overlap construction and check whether it has some maximal superposition space or not. The important point is that we have to check whether it has some lambda mean and our psi I tilde equal to 1 over d. So both of them is if both of them is satisfied, then this state is possibly the golden state. So in the last 1 or 2 minutes, let me add some other works, which is also important for to show the form of maximum states. This is a recent paper on arXiv. I put on arXiv 2 or 3 weeks ago. Here I use Löwding symmetric orthogonalization method. It is very well known in quantum chemistry. For example, if we have a orthogonal or non-orthogonal basis space, then we obtain gram matrix. Then by using this gram matrix, we can obtain an orthonormal basis, which we call Leuden basis. So from a non-orthogonal basis, we can transform this into an orthogonal basis. Here, this transformation can be finalized in this form. Here S is the overlap matrix. Li is the Leuden basis. Cj is the basis of the superposition state. So if we construct this in this form, we obtain these equations. And if we continue in this form, we obtain two equations. If we apply a Leuden symmetric orthogonalization to a superposition state, we can obtain its corresponding form of coherent state. So this is a coherent state, this is a superposition state, and how can we obtain this? We obtain this by Leuden symmetric orthogonalization. What is important about Leuden symmetric orthogonalization? We have it is a powerful tool to obtain the form of the maximally superposition space. What I mean, if you have maximally coherent states, if you perform Leuden symmetric orthogonalization in the opposite direction, you will conclude to obtain the golden states in the case of superposition. So you can apply this for any dimension, for any construction. It is easy to see that Leuden symmetric orthogonalization is a powerful tool to obtain this transformation, to see the existence of maximally superposition states. So to conclude, here in this talk, I discussed about deterministic superposition state transformations, and I discussed golden state for superposition. I also showed the results related to Leuden symmetric orthogonalization, which promises the possibility of more. So there are also, as I said, coherence has a rich literature, but superposition is not. It is relatively new if you compare with coherence. So we have lots of open problems, for example, mixed state superposition transformations or superposition distillation, catalytic superposition distillation. Also, previously, as we showed that the effective role of symmetric orthogonalization to connect coherence and superposition, or to reveal the deeper connection, coherence and superposition, Leuden symmetric orthogonalization has an effective role. So we can go in this way for in the future directions. So thank you for your time.
Okay, thank you, Gökhan, for this very nice talk. We have time for maybe one very quick question before going to the next talk. Does anyone have questions?
I think Christopher have a questions, right?
I think he might just be clapping. I think that's the clapping icon.
Okay. Thank you.
Yes. Yeah, I think yeah, if there are no more questions, then I guess we can thank you again. And,
thank you.
Thank you. Move to the.
Thank you for the opportunity again. Okay. Thank you.
Can you unshare your screen so that the
next sure. Yeah, sure.
Thank you. Yeah, so our next speaker is going to be Christopher Chubb, and he's going to talk about second-order asymptotics for transforming quantum dichotomies with applications to quantum thermodynamics.
Okay, you can hear and see me?
We can see, but the screen is cropped to one corner of the screen. Like we see.
Oh, wait,
Like
is it better now?
3/4. Yes, much better. Good.
Okay, cool, yes.
Okay. So
okay, okay, thank you. And thank you to the organizers for the opportunity to speak today. Right, so yeah, today I'm going to be talking about second order asymptotics for transforming quantum dichotomies. Obviously, I'll explain what that means in a second. And then I'm briefly going to talk about some applications to quantum thermodynamics. So this is joint work with these collaborators here. Patrick and Joseph are in Switzerland, Marco is in Singapore, and Camille in Poland. Okay. So what is a quantum dichotomy to start with? So quantum dichotomy is just a pair of states, right? Nothing more complicated than that. Okay, that's so far so boring. So now what we're going to do is one of the things that we can do with these pairs of states is we can define something called the Blackwell preorder. This is borrowing, some notation that's used classically. So we can define this preorder, which we denote like this, which is some order on pairs of states. And the way that we define it is we say that this pair of states, preorders this pair of states if there exists a map which sends each state to the corresponding other state, right? So ρ1 to ρ2, sigma1 to sigma2, right? Now, obviously, if we only had a single state here, so I didn't have any sigmas, I mean, this would be trivial, this wouldn't do anything. So we need at least two states for this to be a non-trivial statement. Now, one could extend this, which is actually what this is what we're going to look at mostly in today's talk, which is an approximate version of this, right? Relatively straightforward definition. You now just say, well, instead of exactly mapping, I'm going to say that I get close in some distance measure, right? I mean, you can pick any distance measure you want, infidelity, trace norm, whatever. So now the map has to send ρ1 close to ρ2 and close in the sigmas as well, with potentially different errors here, right? And then, of course, one can extend this even further, which is in fact, this is what we're going to look at today, which is now we say, well, we have some sequence of errors and we have some rates, and we want to look at the asymptotic problem where now we're looking at the trade-offs between these errors and the rates with which we can do this transformation, right? So we're asking, what is the smallest error for which we can do this and what is the largest rate for which we can do this? You can phrase it either way. Okay, so this is just sort of abstractly, mathematically, this is the problem that we're going to be looking at to at least gesture in the direction of some physics. What does this actually relate to? So this is the abstract problem, but this actually relates to several resource theories. Can be sort of phrased in terms of these dichotomies. So the first is, and the one that we is thermodynamics, specifically Gibbs preserving thermodynamics, right? So here the free operations are any operations that leave the thermal state, the Gibbs state, invariant, right? And so the way that we can phrase that is we say, well, if both of the sigmas are the thermal state, and I require that the second error is always 0, meaning the thermal state is exactly preserved, and then the first error is whatever, then this exactly captures these so-called Gibbs preserving operations, right? So these transformations, these dichotomies in these parameters reduce to these so-called Gibbs preserving operations. Another is, which is actually a sub-example of this, a subset of this, is the case where you just take the infinite temperature thermal state here, the maximum mixed state. This relates to the resource theory of purity. So again, we're looking at maps that preserve this state with some error, and then we require that they preserve this exactly. So the second error is 0. And then the third is bipartite pure entanglement. Sort of similar thing. It's sort of the exact sort of opposite of this, where you take some product state and some basis state, doesn't matter which. Let's say the 0 state, and again the second error is 0. There is a slight trick here in that this condition is sort of backwards for entanglement, right? So the statement here is that this would be the input and this would be the output. Okay, there's some difficulties to show that you can actually pull these results through, which we looked at in the previous paper, but that's sort of the right basic idea, right? That all three of these resource theories can be phrased in terms of these dichotomies. right? So any results about these dichotomies or transformations of them will tell you about rates in these resource theories. That's the idea. Okay. Okay, some basic notation, which I suppose is probably going to be familiar to most of you. I'm going to use the relative entropy a lot. It's defined like this. I'm also going to use the relative entropy variance, which is maybe less commonly used, which is like a second order version of this quantity, right? If you see this quantity is like the average of this expression here, this is like a variance of it. And then I'm going to use two versions of the Renyi relative entropy, the Petz version, and this sandwich one. I'm also going to use so this is the standard sandwich one. There's something called sandwich one, which is actually going to show up in some situations for alpha less than 0. But okay, the details of that don't matter so much. But this is just the definition that I'm using if you're wondering what's going on with these negative Renyi entropys. Okay. Okay, so I'll just sort of briefly mention what previous results there are in this sort of direction when it comes to these second order asymptotics. So, okay, the first, before we go to second order, is first order. So the first order is relatively simple, which is nice. So here the statement is that if I have some constant error somewhere between 0 and 1, right? I fix the error to be a constant, and then I look at the rate asymptotically, I approach the ratio of these relative entropys, right? Which for notational convenience, I'm going to call C from here on out. In thermodynamics language, these relative entropies with respect to the thermal state can be interpreted as the free energy. So there's a ratio of free energies. And so this is essentially a statement of the second law of thermodynamics, is one way to interpret this. And then for entanglement, you get entanglement entropy. Yeah, okay. So this is the basic idea that you get this, you tend to get this ratio quantity here. An equivalent way of writing it, which it's maybe not straight away obvious that it's equivalent, but if you play around with it, it turns out it is equivalent, is that if I fix my rate to be less than C or greater than C, and I look at the asymptotic error, then it always approaches either 0 or 1, right? In a few slides, I'll show some graphics to sort of suggest why these two things are equivalent. But this is sort of the first order behavior, right? So now we want to go to higher order. So the first, I think, two works on this, there was a paper by Kumagai and Hayashi, and then we had a follow-up paper. So these papers, so this first paper looked at entanglement specifically. So basically it doesn't have these second states here, right? These were just entropies and entropy variances. Okay, in that case, commuting doesn't matter because there's only one state. And here, everything is being done in the infidelity, right? Epsilon is a statement of the infidelity. So here basically what we're saying is we're perturbing this. We're looking at higher order corrections to this statement right here. So here we're saying that as n grows, we still have this constant asymptotic rate. But here we have, okay, these are all just constants, but we have this 1 on square root n correction here, right? Okay, here is, you get this this thing called the Rayleigh normal distribution. The exact expression for this doesn't really matter. But this is the basic idea. You get like a 1 on square root n correction. You can think of it like a central limit theorem type behavior. Right, and so yeah, and then we extended this. The expression that I've written here is the extension to the thermodynamic setting, where you now have these second states. But we required that all of our dichotomies were commuting, right? So rho 1 and sigma 1 commute, rho 2, sigma 2 commute. I know these expressions, right? So that's the main limitation there, and it's an infidelity, which makes the proofs a little bit more annoying, but it's. We also had a second follow-up paper where we looked at the so-called moderate deviation regime. I'll explain exactly what that means in a few slides. But basically here, instead of just looking at constant error, we now are allowing shrinking error, but only sub-exponentially, right? So we have something like e to the minus n to the alpha between 0 and 1, right? So not quite exponential, which is another interesting regime, but anything between exponential and constant we can also do. You get a sort of similar expression, right? You have this constant rate. You have some correction now, which scales like n to this stuff. Okay, the exact expression here doesn't matter, but these two regimes were looked at. Again, commuting, infidelity, the main limitations there. Okay, so the main technical difference today is everything we're going to look at is in trace distance. And it turns out that's going to open up an entirely different proof technique, which is going to be quite nice. One of the major things that you gain is that actually all the results that we're going to show work for non-commuting inputs, right? I make no assumptions about the inputs, but we do have commuting outputs, right? We still require that. We have some of our bounds hold even for general outputs, but for all the tight results, we require commuting outputs. Because of the techniques that we're going to use, they actually sort of quite nicely extend to a whole bunch of different error regimes, right? So I said before that we had, for infidelity, we had results for small deviation, which is this constant error regime. We also could extend it to these so-called moderate regimes where you allow the errors to shrink or grow a little bit. But we can also do the case where the errors are exponentially small, exponentially large, or in fact zero, right? And in some sense, this is sort of all of the different error regimes, right? These all cover all the possible different scalings of the error, which is quite nice. We can also do two-sided error. As I mentioned in the slide about resource theories, in all the resource theories, it only ever makes sense to have the second term have zero error. But actually, mathematically, there's nothing to stop you having an error on the second term. And in fact, we can get some partial results there, even if the applications don't require that. The main advantage from my perspective is the proofs, I think, are quite a bit more simpler, a lot less involved than was for infidelity, which is one of the reasons we're able to extend all these different regimes, which is quite nice. Okay, so that's a sketch of the basic sort of strengths, the result. So the way that we do this, the main technical tool, is reducing everything to hypothesis testing. Right. So I think this is sort of an obvious other task that you might imagine doing with a quantum dichotomy. So now we have, suppose again, we have a quantum dichotomy, we have a sigma and we have a rho, a rho and a sigma. And we could ask about hypothesis testing between these, right? So now, okay, we have some test, which is meant to be indicating that we have a rho instead of a sigma. We can define the type 1, type 2 error. This is probably familiar to most of you. So now there's some natural trade-off between these type 1 and type 2 errors. I can then define the optimal, this beta expression, which is the optimal type 2 error given a constraint on the type 1 error, right? And then optimized over all possible tests. And this is a sort of sketch of what you expect to see, right? Here I just chose, two random qubit states and just generated this function. And so here, okay, if the type 1 and type 2 error can be really large, that's fine. But as I shrink them, I hit some trade-off, right, between these two things, which is this shape here, and that's essentially what this function is describing, right? I'm describing this curve, and so this curve basically describes this optimal trade-off, right? So the really nice thing is not only can we define these two sort of tasks on the level of quantum dichotomies, but they're actually strongly related. So for the case of commuting dichotomy, so essentially classically, there's something called Blackwell's equivalence theorem, which states that I can transform from one dichotomy to another if and only if the beta curve lies above the beta curve of the input. Right, essentially what it's saying. Okay, this backwards direction is quite straightforward to see. Sorry, this forward direction is quite straightforward to see from data processing. The backward direction is not so obvious, but it turns out it's true, which is quite nice. And a quite nice property of the trace norm or total variation distance is that there's actually an approximate version as well. So here the statement is that I have this approximate Blackwell order only if I have a similar sort of expression, but for shifted betas, right? And so what this sort of looks like is now I have the beta curve of my input. Let's say I have the beta curve of my output. So in this case, the beta curve of the output is not above the input, but if I shift it, so this corresponds to a horizontal shift, this corresponds to a vertical shift. If I now shift it, now it is. Right, and so the statement would be for these parameters, then I do have this approximate ordering. And so you can think of these errors as basically saying, how much do I have to shift this curve either horizontally or vertically to get it above. Right. Now, the really nice thing about this is these betas asymptotically have been studied to death, right? In all the various regimes, I mean, that's essentially how our result is going to work, right? We're just going to apply all the asymptotic statements about these betas and all these various regimes and pull this across to tell us about the rates over here, right? That's the basic idea. There's some technicalities in getting that to work to do with this for all and uniformity and okay, but that's the basic idea. Okay. Now, everything I said here is for commuting dichotomies. So, how do we do non-commuting? Right. That's one of the main features that I mentioned is that we can deal with non-commuting inputs. So, right, as I state here, it's known actually that not only does the proof break, but in fact, it's known that the beta ordering in this way does not actually imply this Blackwell ordering, right? Even the non-approximate version of this is known to not generally be, this is not enough, right? So what we're going to do is we're going to define another sufficient condition. Now for single shot, it may not be good enough, but actually for in these asymptotic regimes, we're actually going to see that this is good enough to get tight results in most of the error regimes, which is quite nice. So here we're going to define this P sigma is the pinch of sigma with respect, the pinch of rho with respect to sigma. And the key thing now is that if I pinch rho, then this commutes with sigma, right? And so now I'm going to define, I'm going to look at the hypothesis test between the pinched rho and sigma, right? So I'm going to define this pinched type 2 error to just be the type 2 error where I pinched the first state. It's now, not symmetric, but that's okay. And so I'm gonna pinch the first states, and then for the second states, I'm just going to assume that they commute, right? In all of our results, we required that they were commuting. So if this is true, then I take, if I have, so instead of this quantity up here, now if I have the pinched type 2 error here, and I have the same expression from before, well, now this commutes because of pinching. This commutes by assumption. So that implies this Blackwell ordering on the pinched guy. But actually, you can show that, well, what does this expression tell us? Well, it tells us there's a map that sends the pinched guy to sigma 2, and to rho 2, and sigma 1 to sigma 2, approximately. Well, okay, I can just map that I get from this composed with the pinch, therefore that also implies that I just have this Blackwell ordering directly, right? That there's this sort of data processing, if you like, inequality of Blackwell ordering, right? If I can do it on something that's already been acted on, then I can do it on the raw state itself, right? So this gives us a sufficient condition. So in other words, we have the Blackwell ordering, the thing we care about. That implies this beta ordering, and it's implied by a slightly modified version where you pinch, right? But similar sort of expression. Now in the single shot, these two expressions could be very far apart, right? This would be a potentially crude bound, but it turns out asymptotically, this pinched beta is actually going to have very similar asymptotics to this. In fact, it's going to have the same asymptotics 2-second order in all but one error regime. Which is going to allow us to get tight bounds on the rates here. Okay, so I sort of mentioned small, moderate, and large deviation as sort of regimes of these second order asymptotics. Just a quick sketch. You aren't familiar with this sort of notation. So here we want to look at the trade-off between rate and error as we increase the number of copies, right? So intuitively, low rate, we have some complicated mess, and then as we increase the rate, as we increase the number of copies, I should say, what we sort of know from the first order is that this should sort of naturally approach a step, right? This is obviously a sketch, but this is the idea that we approach this step behavior at the asymptotic rate here, right? And so again, so the first order statement is just that we approach a step. All the second order statements are, okay, how quickly do we approach this, right? Well, there's multiple ways you could quantify that convergence. The first, and this is the regime that is often referred to as second order, but I think in some sense you can think of all three of these as second order, is the so-called small deviation regime. Here we fix the error, we look at everything horizontally, and we look at how quickly the rate approaches the asymptotic rate, right? So we're looking at how quickly these curves are moving horizontally. So here we have constant error, and we expect a 1 on square root n behavior. Another regime is this large deviation regime. Here we fix the rate to be something either below or above the asymptotic rate, and we look at how quickly the error approaches either 0 or 1. And we generally expect it to be exponential. Okay, and then there's this sort of weird intermediate regime called moderate, which is somewhere in between, right? We're approaching the asymptotic rate, but we're doing it, slower than 1 on square root n, and we're approaching 0 error or error 1. And okay, this is just sort of a gap that's left between these two regimes. I think the large and small are the more sort of easy to motivate regimes, more natural regimes, but yeah, we can actually do all three of these, which is quite nice. And as I said, for infidelity, only these two regimes on the left have been looked at. Large has not been looked at. Okay. Okay, so now I'll get into the results. Okay, the exact details of these expressions don't matter so much, but basically what we find in the small deviation regime is a very similar to expression to what was previously found for. So here we have the asymptotic rate. We have this correction involving these entropy variances, again, a 1 on square root n behavior. But here, this quantile function we get, as with infidelity, we don't have a Gaussian term, as you might expect. We get some slightly more complicated distribution here, which is related to the Gaussian, but is not the Gaussian. But here we actually get a different distribution. So in the previous result by Kumagai and Hayashi, they got something called the Rayleigh normal distribution, which sort of interpolates between the Rayleigh distribution and the normal distribution. Here we get something that we call the sesquinormal distribution, which I've sort of given an expression of here, which actually interpolates between the normal and the half normal, which is slightly interesting. We also have a way of writing an expression for what you get here explicitly in terms of the distance measure you use, which actually reduces to the two existing results, which is quite nice. But, yeah. Okay, we can also do the moderate deviation results. These are actually identical to the infidelity results, it turns out. Okay, the details of these don't so much matter, but now we can do that in tracenorm, which is quite nice. Okay, and then we approach the wall of text. Okay, so then we can also do large deviation. Here, the results are not so straightforward, but I present them nonetheless. So in the high error case, we have an error exponentially close to 1. Okay, this expression isn't too bad. We get some. So now we get the Renyi entropies are showing up, sandwiched and pets, and we get some optimization of these expressions. In the low error case, things are a little bit more complicated. We actually, first of all, here we have a two-sided bound. We have the asymptotic rate. Here we have two bounds, but they're actually not generally the same, right? So we have a bound on the lim sup and lim inf, but these for non-commuting states are generally different. And again, you get these sort of expressions involving Renyi entropies, now optimized over a bunch of different regimes, and then you take an inf. Okay, but the very similar sort of expression morally to this higher expression. Okay, so you get something involving Renyi entropes is sort of the idea. And obviously, if everything is commuting, these tildes don't matter. Sandwich equals pets. Everything collapses down, and we get type bounds in this regime as well. Okay, I have a few minutes, so I'll just briefly sort of mention one of the really nice things from an application perspective that you get, of course, now is that I'm allowed to have coherent inputs, right? All the previous results were only ever looking at commuting input and output. So if we wanted to look at applying this to thermodynamics, that's pretty limited. We could only look at so-called energy incoherent states, which commute with the thermal state. Now, for our results, that's still true of the output, but the input is allowed to be coherent. The input is allowed to be general. So now we can ask questions of, well, what if we look at some states and we vary them by their coherence? does this actually affect things? So here, okay, this is the block sphere. I think the red dot here, yeah, the red dot here is the thermal state. The blue dot here is the target state. And then we want to look at these row ones, which are anywhere on this white dotted line, right? We're varying it by coherence. All the same energy, but different coherence. And we could ask the question, okay, if I want to run them at the asymptotic rate, what is the error associated with that transformation? And so what we find is that there are these sharp dips. We had a previous paper looking at this phenomena. We called it resonance. But in this coherent case, you actually can get, quite complicated behavior where you have multiple resonances, which is quite nice. So as I vary along this line, I'm getting that my error is dropping really dramatically and then picking back up and dropping down and so forth. So these coherences can vary the errors quite, which is quite interesting. Okay, so I'll just come to a summary slide. So yeah, so we showed that we can do second order asymptotics for these quantum dichotomies, and rather nicely, we can do it in all the various error regimes. I think I didn't mention zero error, but we can also do that. So in some sense, we can do every single error regime, which is quite nice, at least to second order. We have tight results for general inputs in all but one regime, and then obviously if everything commutes, everything's tight, and then we have one-sided bounds for general input-output. And one thing that I hinted to, but obviously we haven't looked at in much detail, is this obviously opens the door to studying the role of coherence in things like resource theory in these asymptotic settings, where up until now everything has had to be commuting. Yeah, so I'll leave it there. Thanks.
Okay, thank you, Christopher, for this very nice talk. Are there any questions?
Okay, I have a question. So could you please go through the page of the main results?
Which ones? These ones or?
Yeah, okay. So does this, so you mentioned that the results, if I understand correctly, it was for general rho 1 sigma 1, but need rho 2 and sigma 2 to be commute, right?
Yes, that's correct.
So how about the next page about the large deviation results?
Yep.
Do you still need rho 2 and sigma 2 to be commute? So
yeah, okay. So the actually in both of these, so yeah, okay. That, I mean, you might have wondered why I'm, for example, putting a tilde on this expression here. If these are commuting, why does this matter? So in all of these results, so let's come to these small deviation results, for example. The upper bounds that I've written here hold for general input, output, everything, right? They just hold from data processing, right? So if you just look at the upper bound here, that's fully general. The achievability, the lower bound, for that we require the second pair is commuting, right? So
I see.
So here, when I write this sandwiched expression here, I've written that because, well, if these are general, then actually this upper bound here, that does hold still for general states. The lower bound, that requires the outputs to be commuting. Yes. Okay, I see. So also for high error case, I mean, the result in the left side, you also need rho 2 sigma 2 to be commutative. For achievability, yes. For optimality, no. Right. So the upper bound, and here we have an upper bound and a lower bound, right? Yeah. The upper bound is general. Okay. Yes. I understand that. Yeah, it looks very interesting. Okay. Thank you for the answer. I mean, it is to give you the slightly the details of, and basically it comes down to this expression, right? Like obviously this leg of it, I don't need any commuting assumptions, right? This is where we get optimality. And then here, okay, here we start using commuting, right? This is where we get achievability, right? So this,
okay,
this way,
interesting.
yeah, that's the basic idea. Yeah.
Okay, thank you.
Thank you.
Okay, so let's thank Christopher again.
Thanks.
And now our next talk is going to be by Bartosz Regula, and it's going to be about overcoming entropic limitations on asymptotic state transformations by gambling with quantum resources. Bartosz could share his screen. Thank you.
Yeah. Okay. Okay. Thank you very much.
Go ahead.
Yeah, you can hear me. Yes, everything's fine.
Yes.
Okay, yeah, just double checking. Okay, yes. So today I will be talking about how to overcome the kind of limitations which are often thought to be fundamental based on relative entropies through the use of so-called probabilistic protocols. And this is joint work with Ludovico Lamy and with Mark Wilde, and it is available on the archive. Okay, so let me just jump straight into it. What is happening here is that we are concerned with the transformation of some state rho into some other state omega. We want to convert one state into the other, but of course the operations that we can do are somehow constrained. So I will be referring to them as the free transformations, the ones that we are allowed to perform. And so in the kind of our favorite IID setting, we often look at what happens when we have access to more copies of states. So what this looks like is that we have some machine that prepares many copies of the given state rho. Then we plug them into some protocol, and this protocol is supposed to output states which are, let's say, approximately equal to this target state omega, and then we can impose some other conditions on this error. So the well-known kind of rate in standard quantum Shannon theory is defined as follows. It is, again, in this kind of setting, when we have many copies, we are looking at what happens in the limit of n going to infinity. So essentially, what is the largest number such that we can transform n copies of rho into Rn copies of omega with the error in this transformation quantified by the trace norm going to 0. So this is kind of taken for granted in most applications of quantum Shannon theory, but let us look at what this actually means. So what this does is it takes into consideration the number of copies. So the only cost in this kind of framework, the only kind of thing we're paying essentially in this transformation is the number of copies. So the rate asks how many copies of rho we need to generate, such that at the end we will have desired some copies of the state omega. Now, the problem with this is that this never takes into consideration how difficult it is to actually manipulate n copies. So it allows us to generate many copies as long as we pay for this kind of cost of generating them, but then essentially it assumes that we can manipulate them for free. But I mean, obviously in practice, both of these things should be kind of costly. One should be number of copies of the given state, but also the size of the quantum memory needed to actually transform these states. And Shannon theory essentially ignores the second aspect. And of course, this is, in general, Shannon theory is like an idealization of an approximation of the practical setting. But the thing is that in most practical scenarios, generating the states is actually the easier thing to do. So we can actually create many copies of states, but actually coherently transforming many copies, that is where the difficulty lies. So in this approach, we propose to do essentially the opposite. We will ignore the number of copies needed and focus only on the size of the quantum memory, which is required to transform these states into the desired output states omega. Now you might think this is just the same thing, but if you think about this carefully, what we are doing now, we are only paying for the cost of this protocol, the size of the protocol. That is the only kind of the cost function of this transformation is only the size of the protocol. So what we can do for free without any additional cost is to repeat the same protocol, because we are not paying for any number of copies. We can keep creating copies of rho for free now. Essentially, we are taking the limit as n goes to infinity anyway. So we are only concerned with what is the size of the quantum memory, or how large of a coherent transformation we have to be able to perform. But once we are able to perform it, we assume that we can repeat it. And okay, so what does this change at the level of the rates? The level of the rates, you might remember, this is the kind of definition of the usual rate. We have some channels which transform the states rho omega into, rho tensor n to omega. What we can do now is apply not just quantum channels. What we can do now is apply probabilistic protocols. So now we will assume that these are no longer CPTP maps. They no longer have to be essentially trace preserving. They can be trace non-increasing probabilistic maps. And essentially, we don't care about the actual probability of success of this protocol, because we are not paying for the number of copies of rho in this transformation. So we can just keep repeating the protocol until it succeeds. And we are only paying for the size, again, of this protocol that is required in the transformation. So this is the fundamental definition. Definition we'll be using is the probabilistic rate of rho to omega. It is defined using these operations, which are not necessarily trace preserving. We will also be looking at the strong converse rate defined in the same way. So essentially, we don't impose the error to go to 0. We only assume that it doesn't go to 1. This is the usual kind of definition of a strong converse. We just generalize it to probabilistic protocols. Okay, so having defined this, how do we usually study transformation rates? Well, usually what we do is we use entropies to constrain rates. So let us kind of look at how these things are defined. So divergences of relative entropies are a very commonly used concept, and the most kind of well-known relative entropy is the quantum relative entropy, or the omega Q relative entropy. And in settings such as transformations of quantum states in restricted settings, we often encounter the relative entropy of a given quantum resource. So here, essentially, what we have is some kind of set of states which has been singled out as the free states of the given kind of setting. And if we minimize this entropy over these free states, we get a monotone, a so-called Ries's monotone. And for example, the most commonly encountered example of this function is the relative entropy of entanglement. So we have minimized over all separable states. And the point of this kind of definition is that this is a monotone. So for all free operations of the given theory, or free channels of the given theory, this cannot increase. And this allows us to essentially apply it in kind of like constraining transformation rates. So kind of following this idea will be essentially the free operations that we consider in this work, which I haven't still defined, is now, this will be a definition, that essentially a free operation is any transformation which takes a free state to a free state, probabilistically. Here we don't assume this CPTP transformation. So essentially, this is a very kind of like a relaxed definition of the free operation, because, for example, for entanglement theory, this includes the well-known cases of like local operations and classical communication, but also larger sets of transformations. So essentially, we want to make as few assumptions as possible at this stage. But the crucial point is that under any such transformations, whenever they are quantum channels, then this function will be a monotone. This relative entropy will be a monotone. Okay, so now if we want to apply this to constrain rates, asymptotic rates of transformations, we have to consider the so-called regularized relative entropy, which is defined essentially as the limit of rho tensor n, the entropy of rho tensor n as n goes to infinity. And then there's a very well-known result, which has appeared in many different papers. I believe this is the first one, but maybe not. Maybe it's probably people knew about this even earlier. Is the aspect that is the fact that every rate, deterministic transformation rate, is upper bounded by the ratio of the relative entropies. So essentially, this single function, this kind of we take this function, evaluate this at rho at omega, and we can immediately get a constraint on the kind of the best achievable rate in this setting. Now, of course, what we would like to do is to generalize this kind of approach to our probabilistic transformations that we consider in this framework. But the reason why we cannot apply this approach in the probabilistic setting is that the relative entropy is not a monotone anymore if we consider probabilistic maps. So essentially, now we are dealing with transformations that are no longer CPTP operations. And for such transformations, this is no longer monotone. So we need a different monotone. We need just to follow a similar kind of conceptual idea, we need a different monotone to apply the same, to get the same results. So to define such a monotone, we first look at the so-called max relative entropy, which is a very commonly encountered function. It is defined as the essentially the least coefficient such that the state sigma upper bounds the state rho in the positive semi-definite, with respect to the positive semi-definite cone. Now, this function is very commonly encountered in quantum information, but usually in one-shot setting. So it doesn't appear by itself usually in asymptotic kind of constraints, but rather in one-shot constraints. And but of course, we can define here the kind of in the same way the minimize the kind of like a Dmax or max relative entropy of a resource. And interestingly, kind of the fundamental connection between the max relative entropy and the quantum relative entropy, the Omegaki relative entropy, is the fact that if you take the smooth regularized max relative entropy, so if you not only regularize it, so not only take n going tensor copies of rho going to infinity, but also smooth it in an epsilon ball around rho tensor n, then we actually get the quantum relative entropy in the limit. So this Dmax of a given resource, it converges to the quantum relative entropy of a given resource if we allow this smoothing and regularization. So there is a very fundamental connection between the two quantities. Now, okay, so having defined Dmax, now we will use Dmax to define a monotone, which finally will be able to constrain transformations also in our probabilistic setting. And that function we will be using is the projective relative entropy, or the Hilbert projective metric, and is defined as essentially the sum of Dmax of rho versus sigma and Dmax of sigma versus rho. So it's like a symmetrized version of Dmax. And well, this idea, of course, dates back to, well, Hilbert, but in quantum information, it was first applied by David Reeb and others in a paper that essentially dealt with transformations of quantum states, but hasn't looked at resource theoretic transformations like we do in this case. So indeed, we can define this kind of like a projective relative entropy of a resource. And the crucial aspect of this function is that this is a monotone for every probabilistic transformation. So it doesn't matter, the probability here doesn't matter. For every probabilistic operation, for every completely positive operation, even this essentially is a monotone. So it cannot increase. And yeah, of course, we can define the same kind of like a regularized variant of this quantity. But since this is based on Dmax, which is like a one-shot quantity, as I mentioned, and the connection between Dmax and the relative entropy is with the smoothing. So we could ask, of course, what is the smooth regularized version of this projective relative entropy? And I want to stress that this is a priori, this is not immediate, not clear at all, because this function is very differently behaved from Dmax by itself, because this other term can be huge. And indeed, I mean, Dmax between two states, as you might remember from the previous slide, is only finite if the support of rho is included in support of sigma. So in this case here, this quantity will be only finite when rho and sigma have the same support. Okay, for every other case, this will actually diverge to infinity. And in general, this term can be huge, and this quantity can be very different from Dmax at the level of one-shot quantities. But our first result is actually that if you allow this smoothing and regularization, this converges also to the quantum relative entropy. So even though they are so differently behaved, the quantum relative entropy of Dmax versus the projective relative entropy, actually with the suitable smoothing, we get the same quantity asymptotically. And so how does this happen? The main proof idea will be to use the known result that Dmax by itself, it goes to the quantum relative entropy, the regularized quantum relative entropy asymptotically. And what we can do here is we can essentially choose this kind of optimal sequence of free states. So these are optimal states, these rho prime n are optimal states in the epsilon ball of rho, while these sigma n are optimal free states in the definition of Dmax. And essentially, okay, I want to stress Dmax and the projective relative entropy are very differently behaved. So we cannot just immediately take this sequence and apply it for the projective relative entropy. But what we can do is try to, well, identify the sequence and grab onto it and try to find a way to asymptotically go to the same thing. And that is what we will do. So we define a new kind of sequence of states, which are defined as follows. So we have this kind of definition, and this parameter eta is based on this epsilon. And epsilon, you might remember here, it goes to 0. So this quantity will actually be very large. And then, so this state omega n, these states omega n will actually be very close to rho prime n. And again, rho prime n is very close to rho tensor n. So what we get is that this omega n will essentially be very close to rho tensor n itself. And we can show that this asymptotically, it goes to relative entropy, the regularized relative entropy of the given resource. And by essentially, so this optimal sequence allows us to indeed reach the optimal value of quantum relative entropy asymptotically. Yeah, so that's the basic idea. Having kind of established this, now we can finally go back to our probabilistic rates and establish general restrictions on these asymptotic rates. So our our results on the converse bound is that every transformation rate in this probabilistic setting, so using any probabilistic protocols, is upper bounded by the ratio of the projective relative entropy regularized and the quantum relative entropy, the omega k relative entropy, also regularized. And just, I mean, to clarify the difference between this and the kind of the relative entropy bound, what we know is that in the deterministic setting, every rate is upper bounded by the ratio of the relative entropies. But what we have shown here is that in the probabilistic setting, a bound we can get actually only has the same denominator, but a different numerator. So, and this quantity can be very, very much larger than the relative entropy. So these bounds are very different from each other. The main idea again for the proof is to use our first result, which is the asymptotic equipartition property for the projective relative entropy, and then combine that with the monotonicity of this quantity for all probabilistic protocols, and then we play around with the errors a bit, and the result follows. So of course, this is a converse bound, but we haven't discussed how tight it is, and that's a fundamental question to answer. So to talk about achievability of this bound, let us first make an assumption or constrain ourselves to a specific type of quantum resources. These are so-called affine resource theories, and an affine resource theory is defined such that the set of free states contains all states in the affine hull of the set of free states. So essentially, there's some affine space, and in this affine space, all states are free. And this includes, for example, the resource theory of coherence, or thermodynamics, or asymmetry. And in every such resource theory, we get that the rate of transformations under these kind of the free transformations that we consider here is given exactly by the ratio of these entropies. So what this means is that there is no better bound possible. This bound is actually the tightest possible bound, this exactly gives us the transformation rate in this probabilistic setting of our work. Now, the main idea for the proof is to use the fact that the existence of a transformation which maps two states, essentially, it can be reduced to just monotonicity of the single function, the single projective relative entropy. It characterizes this at the level of one-shot transformation. So essentially, we take this one-shot result and we turn this into an asymptotic sequence of protocols which achieve our desired transformation. But of course, not every resource theory of interest is affine. So what we would like to understand is other examples for which this is achievable. And one fundamental example for which we can show achievability is entanglement distillation. So in entanglement distillation, the target state, omega, is just essentially the Bell pair, or the 2-qubit maximally entangled state. And here we can show that for every state, for every input state, the rate of distillation, or the rate of transforming rho into the Bell pair, is given by the regularized projective relative entropy with respect to a set of separable states. And one interesting aspect of this is that in the deterministic setting, we don't have such a formula. We don't have a formula that works for every input state rho. And here in the probabilistic setting, we were able to establish a general formula for the distillation rate of every input state. The idea will be similar as before. The fact that we don't have now if and only if conditions for the existence of transformations in the probabilistic setting, but what we can do is use a similar kind of condition, which is based now it's no longer based on just the projective relative entropy. It uses a slightly different function. I don't want to go into details about this now, but if you are familiar with these research theoretic kind of definitions, this is essentially equivalent to the fact that the standard robustness of omega, or for this particular case of omega, is equal to the generalized robustness of omega. And these there are two different monotones for resources, and when they are equal, this allows for some simplifications. And in this case, we can show they are known to be equal for the maximally entangled state, which allows us to essentially to get a nicer achievability bound. Now, to look more closely at what this entanglement distillation example shows us, let us look at the fundamentally important case of isotropic states. So isotropic states, okay, so we want to understand the rate of distillation from an isotropic state. And what we can show is that in our setting here, the probabilistic rate, this projective relative entropy will actually be additive for isotropic states. So we can compute exactly this asymptotic rate of transformation. And the regularized relative entropy, the standard kind of quantum relative entropy of isotropic states also is known. It is known to be given by this function, but we can show that, I mean, these functions are almost never equal, except for trivial cases. So we have a strict inequality here, but we know that the regularized relative entropy upper bounds every deterministic rate. So we have a strict inequality between the probabilistic rates of our setting and the deterministic rates of, well, the conventional kind of transformations in Shannon theory. And if we plot this, actually, the gap can be quite significant. So here, if you look at the very bottom of this plot, we have the distillation rates plotted against the parameter P of the isotropic state. And if you look at here, the deterministically achievable rate all have to be rates, all have to be in this kind of regime here. But our projective relative entropy bound is given by this red line here. And this is the tightest, it's achievable bound. So it actually is possible to reach it, and so every protocol in this regime is achievable, but only in this probabilistic setting. So we should see that we can strictly go beyond kind of the usual Shannon theoretic regimes. Now, the case of distillation is particularly interesting because we can obtain some stronger bounds for distillation, and our final result will be about a kind of constraining distillation protocols. And in distillation protocols, essentially, what we now want to understand is error. The trade-offs between the errors of distillation, so the error in the kind of target state, how far it is from the desired state, some pure state psi, and the rate of the transformation. So we show a general kind of upper bound, or like, well, a trade-off essentially between the rate and the errors here. And so I don't want to kind of go too deep into this bound, but I want to give you two immediate consequences of this result. First is that our bound is actually a strong converse. So the bound based on the projective relative entropy is actually a strong converse bound for the case of distillation. So essentially, if you exceed this bound, the error has to go to this rate. If you exceed this rate, then the error has to go to 1. So essentially, every protocol is useless beyond this rate. And one other interesting consequence is that there is no super exponential error decay. So this allows us to look at how fast the error can go to 0. And it cannot go to 0 too quickly. Okay, so this formula, it forbids an error that goes to 0 super exponentially. I mean, okay, it forbids when this quantity doesn't, I mean, when this whole thing, it might trivialize, because there are cases, for example, for pure states, when this actually is infinite. So whenever this is not infinite, then we get a constraint, which is non-trivial, for example, for all full rank states. And it shows that there is no super exponential error decay even in this probabilistic setting of our work. Now, just want to clarify kind of here, because you might be familiar with rates that look like this, which are, for example, used very commonly in understanding entanglement transformations and, for example, connections with tensor ranks of pure states. And these transformations, they use, for example, LOCC transformations in entanglement theory, and they don't allow any error. Okay, so this transformation between two pure states, psi going to phi, is exact. So there is no error there. what we show is that this definition cannot be applied when this input state is not pure, or well, it is when it's highly mixed. We cannot do this anymore because there has to be an error, and this error cannot go to zero too quickly. So we cannot just take, this is a zero error definition, and there is essentially no possible way to define a zero error rate for highly mixed states, even in this probabilistic setting. This is one consequence. Okay, so just to conclude, what we have established is general constraints on all possible probabilistic protocols. And I want to stress why this is non-trivial, because we have changed the definition of a rate. We have gone beyond conventional Shannon theory. So a priori, it's not clear if there should be any constraint. Maybe every rate becomes achievable. We don't know what happens in that regime, but we have shown that there are general constraints that every rate has to obey, and we have exactly characterized them using this projective relative entropy. Now, in many cases, we have shown that these are actually the best bounds possible, so they are achievable in many cases. And indeed, we have shown that they can be strictly larger than kind of the well-known relative entropy bound. So this approach goes strictly beyond Shannon theory. Okay, and one follow-up question which you might have immediately, and at least, well, we had, is, okay, so before the quantum relative entropy was known as the bound on transformation rates, it was known as the error exponent of asymmetric hypothesis testing. And this is often considered the kind of the fundamental operational interpretation of the quantum relative entropy. And one could, of course, ask, is something similar possible in the setting of our work? Is this projective relative entropy relevant in a similar way? And indeed, in a very recent work, essentially a follow-up work, we show that well, one can define a task of hypothesis testing in which this projective relative entropy plays the same role as the quantum relative entropy. So these are really kind of like two fundamentally kind of similar quantities. One open question which we have not been able to show to prove is the kind of beta bounds when peer-to-peer transformations are considered, for example, under LFCC operations, because as I mentioned, pure states are very differently behaved when we do these kind of probabilistic operations, and our bounds are not able to recover some of the results which are known for pure state transformations. But I don't want to make this seem like a limitation of our results, because I believe that the kind of the more noisy case is more useful in practical aspects. But conceptually, I think it's very interesting to understand exactly the relation between peer-to-peer transformations and mixed transformations, and we don't have an answer yet to that problem. So that's an open question. And with that, thank you very much for your attention.
Okay, thank you very much, Bartosz. So I'll open the floor for questions. I think Nilanjana has a question.
Hi, Bartosz. Thanks for a very interesting talk. Something I don't personally know a lot about, just want to throw the question out there. People have studied SLOCC entanglement conversions, right? Stochastic LOCC. So does that fall in your framework? And if so, is the result for entanglement, distillable entanglement that you get, match what they would get for SLOCC?
Yeah, so I didn't want to go into kind of SLOCC because I wasn't sure if, this rate that I showed here at the bottom is essentially usually considered under SLOCC operations. This is essentially in this works. For example, Matthias Christian looked into this kind of tensor ranks and kind of relations between SLOCC transformations. So this is exactly what I was talking about here. People have looked into SLOCC transformations, and SLOCC is a subset of the operation that we consider. So all of our bounds are also upper bounds on what you can do with SLOCC. But one could potentially hope to get better bounds for SLOCC under some constraints. So I think that our bounds will be generally very strong and probably tight-ish for highly mixed quantum states, for full rank quantum states. But for pure states, one could hope to obtain better ones, and that's what people have done previously, mostly focus on pure states with LOCC. So yeah, so to answer your question shortly, yes. I mean, our approach is more general, but for pure states, it's actually too general, maybe. So yes.
So is it known what the distillable entanglement is for mixed state under SLOCC? And if so, do you get an achievability with your result?
I don't think it's known exactly what it is, except for pure states. For pure states, given by there's the tensor rank again comes into play.
Yeah. Okay.
But For mixed state, I don't think there is anything known. And no, our results, our achievability results are strictly for non-entangling operations. So this is the only achievability results we get. So that's a larger set of operations than SLOCC, yeah.
Yeah, indeed. Thank you.
Are there any other questions? Anyone? Maybe I have a quick one. Can you say a bit more about this post-selected hypothesis testing you mentioned at the very on the last slide?
Right. So post-select. So essentially, yes. So this is something essentially we did as a way again to understand the meaning of this projective relative entropy. And so in conventional hypothesis testing, essentially we have a measurement which has two outcomes. We guess one state or the other, and then we understand the errors of this transformation. And in this post-selected hypothesis testing, what we do is we allow an additional outcome that is like an inconclusive outcome. And so if we get that outcome, we essentially ignore this result, and we only look at what happens for the first two measurement outcomes. And so the post-selection happens because we have to essentially we have to condition on the conclusive outcome. We have to disregard all inconclusive outcomes, and then if we condition on this conclusive outcome, so essentially we consider three outcome measurements, but we ignore all the third outcomes. Essentially, that's what happens. And in that setting, it is remarkable because essentially all the calculations which are known for channel theory, they simplify a lot. Everything becomes much easier. And for example, there are no second order terms, for example. All the second order theory that we've just heard about, it is completely irrelevant for this post-selected setting because all the rates, they only depend on the first order terms, essentially. And in this setting, we get exactly as the kind of the exponent, as the error exponent, we get this projective relative entropy. So if you want to look at more detail, I mean, I don't have the formulas here because it's a different paper, but if you want to look into more detail, then we explain this in this recent archive preprint.
I see. Thanks a lot. So let's thank Bartosz again. And now I believe there's a group photo, so maybe I'll let Masahito take over.
Yes, now we have group photo session. So please show your photo. Please show your video. So then we will have some photo. Oh. Hello. Still, some people does not open the photo. So please open photo. So only half. So not enough. So why you are so shy? So please show your face. Still so many persons. Why? Maybe depend on country. Somehow in China, almost impossible to open due to the bad internet connection. But so in the worst case, you don't need to move. So in the worst case, somehow you are how to say face is freezed. So this one does not make problem. So we need your face. So somehow freeze is okay. So
I see many faces, Matsuhito.
Yeah.
I think we're pretty much all showing ourselves.
So then this is enough. So still several
I think so.
So then I will take a photo. So 1, 2, 3. Hello. Okay. I take one photo. Okay. I take another photo. So this is okay. Still several persons does not show your face. So
Masahito, I see everybody with the camera on. So maybe you don't see the same thing as we do.
Everything. I'm confused. So I cannot understand.
Yeah, I see the camera on for everyone as well. If you look at the participant list.
Everybody.
I took some photos, Masito, so I think we should be good.
Everybody already photo on. So, but in my side, not everybody. So maybe I'm not a good person. So somebody please take a photo instead of me. And later, please put on your photo on the
I took some photos. I'll send them to you.
Oh, thanks. Okay, thanks. Maybe I will use this one. Okay, thanks.
Yeah, and some on Twitter.
So please put by using the chat. So okay. Okay, maybe we can finish photo session. So maybe already many people take a photo. Okay, so please send it to me. Thank you very much. So now we have a break until どうしようこれ何や9 o'clock. So we have a 30 minutes break around. So also I will arrange breakout room. So maybe if you want to discuss with several persons, you can use breakout room. So thank you very much. So, なんてこった。どうなんか。そう。
Can you see the cursor?
I can see the cursor, but this is not the first slide though. It's
Yes,
the third
sir.
one. I see. Okay, great. Yeah, now it's everything is fine. Okay, then sure. Are you ready to start?
Yeah.
Great. Then, welcome back everyone to the last session of the day. So the first speaker will be Marco Fanizza, and he will tell us why quantum theory in finite dimension cannot explain every general process with finite memory. So please, the stage is yours.
Thank you. Hello, everyone. So this is a joint work with Joseph Lumbreras.
Recording.
I think it is, right? Or not yet?
Wait. We did
or maybe not.
Recording. So by make a recording. Okay, please start.
Okay, hello, everyone. Yes. So this is joint work with Joseph Lumbreras at CQT and NUS and Andreas Winter. We are both at UAB, and we just put the preprint on archive. So what we study in this paper are linear models of stationary stochastic processes. So I will start by defining what this means and giving some properties of these models, and in particular mentioning an interpretation of these models in the context of general probabilistic theories. So once you have such interpretation, you can ask which kind of theory supports these stochastic processes, and it could be a classical or quantum or a general exotic model. And so an important question is to understand the differences in expressive powers of these classes of models. And so after giving the necessary background, I will show a sketch of the proof that quantum models are in fact insufficient. So let me start from the definition of stationary stochastic processes. Here we consider an alphabet with a finite number of symbols and the set of all possible words of arbitrary length, including the empty word epsilon. And we focus on stationary processes. That is, we can assign a probability to any word, and it does not matter to which time we start caring about the word. And so this is the stationarity property. And for the empty word, we have that the probability is 1. And so the question is, can we find an explanation of a stochastic process? So a very simple example of how to get and a familiar for you probably example for how to get a stationary stochastic process is to consider repeated quantum measurements on a system with the same instrument. Here, an instrument is described by a set of maps, du, such that their sum is unital, and the probability of a sequence of outcomes u on the state row can be computed by the appropriate Born rule. And going through the Heisenberg picture, then we can rewrite this with this notation, which is convenient since we can read the word from left to right. And taking rho to be a fixed point of the sum of the maps, this probability defines a stationary process. So this notation can be pictorially represented with this diagram, where we see that we start from a state pi of a hidden memory system, which evolves to maps labeled by the outcomes that we get at each step. And after we get the last symbol, we take the inner product of the hidden state with some other right stationary vector. In the case of the quantum models, this tau, this right vector, will be the identity. But now we can abstract from this and forget about the particular requirements for quantum evolution maps, which are CP maps. And if we just insist of requiring this linear structure and this compositional structure of the maps, then we get what is called the quasi-realization of a stationary stochastic process. So a quasi-realization is defined as a quadruple of a real vector space, a vector in its dual, and the function from words to linear maps in the vector space, such that the empty word is mapped to the identity, and the product of maps associated to two words is the map associated to the word obtained by juxtaposition. And moreover, in order to enforce stationarity, we ask that pi is a left stationary vector, is a left eigenvector of this map, and tau is a right eigenvector. And the probability would be computed in this way, which in fact respects the structure of the picture that we had in the previous slide. So these kind of models have very nice properties, and in fact they are quite general explanation of a stochastic process. It can be proved that a finite dimensional quasi-realization exists if and only if the rank of a certain matrix constructed from the probabilities is finite. Quasi-realization of the same process are called equivalent. Quasi-realizations with minimal dimensional view have a special role, and they are called regular, and they are related to each other by similarity transformation. The function from words to maps is given entirely by the single letter maps, making a quasi-realization specified by a finite list of real numbers. And most importantly, there exists a canonical procedure to obtain a regular representation from the knowledge of the probabilities and just linear algebra. So if you want to see more about these properties, you can see the review by Vidyasagar. So The problem is maybe that just asking the structure of that we mentioned for quasi-realization is not enough to define an actual stochastic process, because if you consider an arbitrary set of matrices, you do not have the guarantee that probabilities are non-negative. Instead, if you restrict to models based on classical or quantum dynamics, you have this guarantee. So if you restrict to classical models, then you have what are also known as hidden Markov models, where the hidden state is a probability distribution, which evolves through matrices with non-negative entries. These are also called positive realization. And if you consider quantum models, as I mentioned, you have hidden quantum Markov models, where the hidden state is a quantum state evolving through completely positive maps. And these are also called completely positive realizations. However, even if you don't have such interpretation of the stochastic process, there is still some nice geometric feature that quasi-realization associated to stochastic processes have. And in fact, it's immediate to show that a quasi-realization defines a non-negative measure if and only if there is a convex cone inside the vector space, which is without loss of generality closed, such that tau belongs to the cone is invariant under the maps, and the pi is in the dual of the cone. And we call cones with these properties stables. And in fact, it's hard to check if given a candidate quasi-realization, if this cone exists, it's in fact undecidable. Nevertheless, if you know that such cone exists, then you can have an interpretation as a general probabilistic theory in the context of general probabilistic theory. Here, you would need a cone and a dual of this cone to define a state space. In this case, the state space are the elements of the dual cone, which are normalized through the unit tau. And we also need to define an effect space that gives probabilities which are actual probabilities, so between 0 and 1. And you can do it if you have a stable cone. And then the maps are in fact linear maps on the state space. And at each step, the state gets transformed by this linear map, and the state after the outcome u at time t+1 is obtained by the state at time t, acting with a map du and divided by the probability of getting u. In general, this interpretation as a general, in the context of general probabilistic theory, is not unique, in the sense that a quasi-realization does not immediately identify a unique stable closed cone. But we can put inner and outer bounds on the stable cones from the cones generated by the quasi-realization dynamics. So what can be shown is that any stable closed cone has to satisfy this inclusion. It has to be larger than the cone obtained from the orbits of the right stationary state. And actually its closure, and it has to be smaller than the dual of the cone generated from the orbits of the left stationary state. And so we cannot say much more at this point. So if instead you have the guarantee that there exists a classical or quantum model for your process, then you also have the guarantee that there exists cones with some nice, with some peculiar properties. So already in the early days, it was shown that a necessary and sufficient condition for a positive realization to exist is that there exists a polyhedral stable cone. For the quantum case, there is an analogous characterization in terms of necessary and sufficient conditions given by Monras and Winter, where it's highlighted the role of semi-definite representable cones. And setting this necessary condition, sufficient condition is much more complicated. And for our purposes, what is important is that a necessary condition is that there exists a stable SDR cone. So in particular, these cones are semi-algebraic, that is, they can be defined through a finite number of inequalities involving polynomials of the coordinates. And so here we see a possible attack to show that quantum models are not enough, which is the one that we follow. And it is to search for quasi-realization of stochastic processes where the only stable cones are not semi-algebraic. So before going to the actual proof, let me define the question a little bit better. So we want to understand how expressive are classical and quantum models. So we can define three subsets of stationary processes. So G are the processes which admit a finite quasi-realization. P are the processes with a positive realization, so a classical one. CP are the processes which admit a completely positive realization, so a quantum one. So clearly they have to respect these inclusions. And these inclusions are in fact strict. So P is strictly included in G was proven in the early days by Fox, Rubin, and Darmadikar and Karner. And P is strictly included in CP was proven by Monraz and Winter, and we prove the last statement. So is it actually instructive to look at how P is strictly included in G was proven? Because they initially, the processes they consider were initially defined as functions of infinite dimensional Markov chains. So in this case, the state space is the set of non-negative integers. So the state can be one of these non-negative integers. And what happens is that at each step, if the state is in zero, at the subsequent step, it's in the state L, with this probability for L larger than zero, and which this probability is so exponential in L, and multiplied by this trigonometric function. So when L is not in zero, with probability 1, it goes to the lower state. So from L, it goes to L minus 1. And then the process is generated by taking a function of the current state of the hidden memory. And the symbol that is output is A if the state is in 0, and B if the state is in X. So the key ingredient to show that there is not a classical realization for this process is that the eigenvalues with maximum modulus of a non-negative matrix have phases which are commensurate with pi. And one can tune alpha in such a way that it is not commensurate with pi, and this would imply a violation of this fact if there was a classical realization, a positive realization. So this approach fails in the quantum case because the spectra of CP maps do not have similar restrictions. But it was not known if this process could have a quantum realization or not. And this is why we started considering these processes. But we found out that, in fact, a quantum realization exists on a Q-treat. And this is very interesting because it tells us that hidden quantum Markov models are quite powerful. This is an example of a process which was defined not in a quantum, not starting from a quantum interpretation, but in fact, it has a quantum model. And this class of quantum models that we can find are even more general than the FRDN processes if one does not tune the parameters exactly to produce those processes. But even for different choices of the parameters, they do not admit classical realizations. And in fact, so this is a bit of a lateral point, and I will briefly comment on it. If we consider a choice of parameters where the model are actually qubit models, we can consider a noisy version of the process. And we show that the gap between the classical and quantum memory requirements is even robust if one perturbs the maps with the polarizing noise. In the sense that the number of states of the Markov model must grow with a power law in terms of the noise parameter. If you want, I can tell you more about this. But let's go back to our main question. So the approach based on spectral properties of the map does not go anywhere in this case. So we set out to follow the other approach, which is a more geometric approach, which was used by Monraz and Winter to prove the separation between classical and quantum models. So there, they proved the non-existence of polyhedral stable cones by exhibiting a suitable symmetry that the cone must respect, but which polyhedral cones cannot have. So the question is if we can find a similar restriction to exclude the existence of stable SDR cones in some quasi-realizations of some process. So there is an important difficulty is that a suitable closed stable cone can be in principle any cone between Cmin and Cmax. But this simplifies is Cmin is actually equal to Cmax because then we have just one possible candidate. And this is the idea that we follow. A convenient fact is that if it is sufficient to prove the non-existence of SDR suitable cones in a regular quasi-realization because all the quasi-realizations are related by a linear transformation. Okay, so in the end, what we found out as the simplest example is to construct a quasi-realization over the exponential cone. So the exponential cone is a three-dimensional cone defined through inequalities which involve the exponential function. And in fact, it can also be seen as the cone that one obtains by taking the graph of the exponential function at x2 equal 1 and intersecting with the raised from the origin and taking the closure. The dual of the exponential cone has a similar structure, in fact, and it also can be obtained by taking the graph of an exponential function, this time at y3 equal minus 1, and taking the race that intersects it. And so the simplest example that we have, it's actually a model based on an alphabet of 3 letters. So we need 3 maps. And we find this parameterization of these 3 maps, which is such that there exists a choice of parameters which give such that these maps are such that their sum is unique and left right eigenvectors with eigenvalue 1, which we can call pi and tau. And the resulting quasi-realization is in fact a good quasi-realization of a stochastic process. And the exponential cone is the unique stable closed convex cone admitted by the quasi-realization. And therefore the resulting stochastic process do not admit a quantum realization. So the steps are, first of all, to show the existence of the process. And here we first choose D0 in such a way that mu0 transpose is in the dual of the exponential cone, M0 is in the exponential cone. And with this choice, D0, D1, and D2 are such that they preserve the exponential cone acting from the left and the dual cone acting from the right. And choosing mu appropriately, we have that a unique tau in the exponential cone and pi in the dual exist such that they are also stationary. And the key ingredient here is a generalized Perron-Frobenius theorem, which says that if a matrix leaves a cone invariant, then it admits an eigenvector in the cone with eigenvalue equal to the absolute value of its spectral radius. And so these three ingredients certifies us the existence of a stable cone. So the probabilities that we can define from this quasi-realization are in fact non-negative. And we have also the first inclusion that C mean is inside the exponential cone and the dual of Cmax is inside the dual of the exponential cone. Now we need to show the other inclusion. And we do it by looking at what the matrices D1 and D2 do. So their products can be rewritten in this way, where X is defined in this way. If one chooses the logarithm of A and the logarithm of B with different signs and to be incommensurate, when S and T vary in the natural numbers, X becomes dense in R. And so we can explore all the values of X. So the other matrix D0 is such that at some point, since it's a rank 1 matrix, it works that at such point, the stationary state will be reset to M0. And therefore, the orbit of the stationary, right stationary state, which generates C mean, has to include also the orbit of M0 under this matrix for all the values of X. And now the nice thing is that we can choose M0 in such a way that its orbit is in fact the graph of the exponential cone and the exponential function, and taking the cone generated by it, we get the exponential cone. So we get the first inclusion in the opposite direction. And but the very nice thing is that we can do the same on the other side. So we can choose mu0 such that its orbit gives the dual of the exponential cone. And so this basically finishes our proof, because now we have that C mean is equal to C max, and they're both equal to the exponential cone, which is the only suitable cone, and it is not semi-algebraic. And so there is no quantum model. Okay, so what we have learned from this is that hidden quantum Markov models are expressive enough to model interesting processes, such as the one defined by Fox-Rubin, Damatic, and Kearney, which are not natively quantum. And there is also a gap in terms of memory requirement. I mean, this gap can be robust to noise. However, hidden quantum Markov models are not universal. And so it is interesting to study other possibilities and to study theories which include both quantum models and these other non-semi-algebraic models, and which maybe can be easily characterized. And for example, we have this example of the matrix relative entropy cone, which is able to support both quantum models and our exponential, our process based on the exponential cone. And finally, since quantum and general models are probably more expressively than classical ones, one question, interesting question, if these models can be actually useful for data analysis with data from the real world. And with this, I have concluded, and I thank you for the attention.
Thank you very much, Marco, for this very enlightening talk. I guess we have time for maybe a couple of questions. So I don't see, yes, in the Slack.
Okay, I see.
Andreas is, right. He just mentioned that you have two related papers on these hidden quantum processes.
Yeah. Masaito, I think, it said to Andreas that we have.
Oh, sorry, Masaito, yes.
So
nice.
Yes, I have two comments. So, indeed, I already discussed similar topic. At least in the same framework, we discussed hidden Markov process, and we evaluated the stochastic behavior. And also, we discussed when we have that kind of stationary state, even in the framework of GPT.
Okay, thanks. I will look at it. Yeah.
So if possible, please check on our paper, our two paper.
I think we didn't notice it. So thanks. And please link it.
I put if you go to that Slack channel, so you can directly download our paper.
Okay, thanks.
At least Andreas can access both paper now.
Nice. What's the are there related results to our?
Yes, somehow, yes. At least we already discussed in the framework of GPT, and we discussed the existence of stationary process in the framework of GPT. This is one. And also we consider that kind of hidden Markov process. So then we discuss that kind of stochastic behavior. In your talk, you did not discuss that topic, but we discussed that stochastic behavior of that output.
Nice. Yes. We just considered these structural questions, but for sure there are many interesting things to study. Yes, thanks.
Okay, so if there's no other remarks or questions, then let's thank Marco for his talk, and we can move on to the next talk. Thank you, Marco. Okay, so it's a great pleasure to introduce Professor Holevo for the next talk of the session. And he will be talking about quantum Gaussian maximizers and generalizations of Loxo-Balef inequalities. Please, Professor. I think we cannot hear you. At least I cannot hear you. Hello? Professor Holevo, I think we cannot hear you. You might have to activate sound, the microphone.
Can you hear now?
Now, yes, perfect. Thank you.
Okay. Sorry. The problem of quantum Gaussian maximizers is not problem of quantum Shannon theory. And it is one of the aspects of this problem is finding explicitly classical capacity of bosonic Gaussian channels of various kinds. And this hypothesis states that the full asymptotic capacity of such channels is attained on Gaussian encoding. After several approximations, iterations, a breakthrough was made in our paper with Giovannetti and Garcia Patron, and also Giovannetti and Mari, where this hypothesis was proved for an important class of multimode Gaussian channels, which are called in physics phase insensitive, and in mathematics gauge or contra covariant. And somewhat later, I extended this solution to a broader class of channels satisfying threshold condition, which has a form of matrix inequality. So this gauge covariance is a kind of equality, and this is matrix inequality. Roughly speaking, this condition ensures that the upper bound for the capacity as a difference between the maximum and minimum output entropies is attainable. At the same time, this hypothesis remains open for a large variety of Gaussian channels which do not satisfy the threshold condition. And here we outline a new approach to such problems, which is based on principles of convex programming, and will illustrate it on a characteristic case of approximate position measurement with energy constraint, which in quantum optics underlies Gaussian homodynamic, and also for Gaussian heterodynamic. And rather remarkably, for these two models, the method reduces the solution of the optimization problem to new forms of the celebrated Bloch-Sobolev inequality in mathematical physics. I hope that these two basic models will reveal a path to a general solution of the hypothesis of Gaussian maximizers. Now, mathematical setting. By S, Gothic I denote by convex set of all density operators in a separable Hilbert space, and X and Y are standard measurable spaces. I define measurement channel as a map of density operators in H into probability densities on the output space Y capital. And I assume that this probability density is given by uniformly bounded positive operator valued function M of Y, operator density, satisfying the normalization condition integral with some fixed sigma finite measure mu is equal to identity operator. This is measurement channel, and encoding for this channel is a couple of consisting of family of states, depending on the input parameter X and probability distribution of this input parameter. Moreover, since the system is infinite dimensional, we must impose energy constraint. So we introduce Hamiltonian H in the Hilbert space and fix some energy level E capital. Then the energy constraint classical capacity of the measurement channel M is given by the following expression. It is just supremum of the mutual information between X and Y, which are given, which distribution is given once I have encoding and the measurement channel is given, and the supremum is taken over all ensembles for which the average state, which is defined in this way, has energy less or equal than E. And it is a result in quantum information theory that this is indeed capacity in the sense of information theory. So there is corresponding coding theorem. But my problem will be computation, explicit computation of this quantity C. Now, I can write it in a different form by introducing output differential entropy. So P rho is a probability distribution of outcomes. So the output differential entropy is this. And under my condition, which I introduced at the first slides, this is well defined. And the Shannon information, mutual information, is given by the following expression. It is a differential entropy of the average state minus average of output differential entropies for the states of encoding. Then we can rewrite the expression for capacity in this form as supremum over difference between differential entropy of arbitrary state rho satisfying this energy constraint and this special function, which I denote em of rho, which is an analog of convex closure of output differential entropy. It is just infimum of this integral over all ensembles for which the average state is given to the fixed state rho. And then we make supremum over rho satisfying the energy constraint. So this is exact expression, and it has an useful upper estimate. It is less or equal than supremum minus infimum of the output differential entropy. And this upper bound is important because it turns into equality in many interesting cases, giving the value of the capacity. In particular, this happens when the maximizer of the first term can be represented as a mixture of pure states minimizing the output entropy. And all the instances where the hypothesis of Gaussian maximizers was solved so far refer to that case. But in the present talk, as I told you, I propose a method which allows to prove, I hope for the first time, the hypothesis when this condition is violated, the inequality 3, this inequality is strict, and hence it is useless, and we have to compute explicitly this convex closure. And the method relies upon computation of this quantity, which I described immediately. And then I illustrate the method on the solution for the cases of Gaussian, noisy, homo, and heterodyning. Our method of computation of this quantity is based on similarity of the optimization problem for computation of E of M, and general quantum bias estimation problem, as you will see. Any encoding we can realize as a probability distribution on the set of all quantum states. It is concentrated on some carrier, but we can also extend this distribution and consider encoding as just a distribution over all set on the set of all quantum states. There is still another equivalent description of encoding. If we introduce such a positive operator valued measure, rho multiplied by P of d rho, it takes values in the set of quantum states. And its normalization is the following. The average state is just the barycenter of the this measure giving the encoding. So it is not a POVM, it's positive operator valued measure, but it is not probability operator valued measure. And what is remarkable that the minimized functional, this is the functional E, which we want to compute, minimum of which we compute. It has the form, the following form: trace integral of some operator valued function K of rho multiplied by P d rho, where P d rho is just this operator valued measure. And K of rho, this function, is defined by the measurement channel through the operator valued density M, and it has the following expression. So it's computable, in principle, it is computable function, which we will compute in our examples. Now, if we fix some average state rho bar, we arrive at optimization problem. Minimize this trace integral under the condition that operator valued measure is positive, and that the normalization is equal to this fixed average state rho bar. And this is formally similar to the convex optimization problem, which arises in general quantum bias problem, where the number of decisions is infinite, and in fact decisions are just density operators rho in this case. The minimized functional is affine in the argument E encoding, and constraints are convex, so it is convex programming problem. And the optimality conditions for such a problem were studied before, and because of lack of time, I will introduce them formally. There are plenty of mathematical detail here, because everything is infinite dimensional in interesting cases of applications. So formally, let me recall that operator valued function K of rho, which is defined in this way, then at least sufficient condition for the optimality of encoding P given by this probability distribution and this family of state is the following. There should exist self-adjoint operator lambda 0, which satisfies this inequality for all quantum states rho, and such that the difference between K of rho 0 and lambda 0 is annihilated by this optimal measure PP0, which means that product with rho 0 must be 0 almost everywhere with respect to the measure P0. And if we integrate this equation, with respect to P0, we obtain the equation for determination of lambda 0. Then the problem becomes to check this inequality for all quantum states rho. Now we will pass to bosonic Gaussian systems, and I denote by S of alpha the set of all states with fixed matrix of second moments, and I will introduce alpha constraint capacity, which is supremum of Shannon information with respect to encodings for which the average state has fixed second moments. And in my previous paper, it was proven that for arbitrary general Gaussian measurement channel, I don't give definition. This is just a quantum classical channel with in the bosonic setting, which maps Gaussian density operators into Gaussian probability distributions. Then the optimizing density operator, which is the barycenter of the encoding, is necessarily Gaussian operator. So the point is that in this problem, we can restrict to ensembles which have average Gaussian state. And this is very general theorem, which is valid for many modes. Of course, this is also for quadratic bosonic Hamiltonian, which quadratically depends on canonical variables. This theorem reduces the problem to calculation of this alpha constraint capacity. Now, first example. This is approximate measurement of position in one mode. And it is given by positive operator valued measure m dy with operator valued density of Gaussian form. And beta here is just the power of the Gaussian noise. And the problem is, as I told you, is to compute this function E of m, and hence the classical capacity for the oscillator Hamiltonian. So we fix oscillator Hamiltonian. In this case, we can restrict to Gaussian states with diagonal covariance matrix. This can be shown. And the result is the following, that alpha constraint capacity in this case is given by this expression, and it is obtained on the Gaussian encoding consisting of squeezed states with the parameter squeezing of delta given by this expression, and distributed the shift parameter x is distributed normally distributed with the variance given by this value of the parameter. Thus, we see that the optimal encoding is Gaussian. Moreover, it encodes the information only into the displacement of the position, and the momentum p is ignored. It is useless to use it. And if we further make optimization with respect to alpha, we obtain the following expression for the constraint capacity of the measurement channel, where E is the energy of the signal, beta is noise. So nothing like signal to noise ratio. Sketch of proof I will skip because I don't have time for this, but essentially it is reduces to checking the second condition and for the Gaussian encoding in question, and then we can find the operator lambda 0. This is Hermitian operator which satisfies the second optimality condition. And now the main problem becomes to check the first condition, that lambda 0 satisfies this inequality for all density operators rho. And it turns out for rather arbitrary unit vectors psi in the underlying Hilbert space. And it turns out that this inequality reduces to a generalization of famous logarithmic Sobolev inequality. Namely, after some transformations, we can show that what we must prove is the following inequality 7, which turns out into standard log Sobolev inequality when beta is equal to 0. And starting from this case, it is possible to prove this inequality and in this way to prove the theorem. Now I have quite a few time for heterodyning, but this is very interesting. Therefore, I will just describe the measurement and then show the corresponding log Sobolev inequality which appears. Here we have POVM, which is just displacement of some fixed Gaussian density operator. It is approximate joint unsharp position momentum measurement, and in physics it is just describes noisy heterodyning with beta Q and beta P intensities of the noises. And then again, the problem is to compute this function EM that is solve convex programming problem. And the answer is given by this theorem. And the main conclusion is the optimal encoding is Gaussian. And here all parameters are given. I have no time to explain. And if we maximize with respect to alpha, we obtain here in the last row the value of constraint capacity with energy constraint E. And it depends on whether or not E is greater or equal than the so-called energy threshold function. So threshold condition in this case is just this inequality. In one mode case, it reduced to scalar inequality. And finally, I want to demonstrate what kind of generalization of log Sobolev type inequality appears in this case. So it contains the entropic term, then some constant terms, and then gradient terms. So I wrote it down and suggested to participants of my seminar, and Sergei Filippov, whom probably some of you know, was able to prove this inequality. So this inequality must hold for every wave function psi of unit norm. And what is interesting is that it combines the gradient inequality and the generalization of the Verl inequality as proved by Lieb, but it is Verl inequality is obtained when beta are equal one half, and this is somewhat more general inequality. So finally, both the proof of the original Verl inequality and the Sobolev inequality given by Lieb and Loss rely upon the sharp version of Young's inequality for convolution with different functions. And in the case when the threshold condition is broken, this is the case of this inequality, we obtain a new type of logarithmic Sobolev inequality, which relates generalized Verl entropy with the wave function gradient. I finished. Thank you for your attention.
Thank you very much for this very nice talk. I guess we have time for one question, perhaps. Maybe I can ask you a question. So at the beginning of your talk, the way you rewrote the capacity was very general. It didn't depend on the fact that you're looking at Gaussian measurements. Could you envision using other types of log-Sobolev inequality to get exact capacity ranges for other types of channels, measurement channels?
Yes, yes, I hope for this.
Okay.
And yeah.
Okay. So Mark Wilde has a question.
Hi, thanks for the talk. Very interesting. Can you say anything about entanglement-assisted capacity of measurements?
Entanglement-assisted capacity is easier than the classical capacity, and it was solved in our paper with Vladislav Yashin a year or two ago. There is no threshold phenomenon there.
All right, thank you.
Okay, so if there's no more question, let's thanks again Professor Holevo for this very nice talk, and we can move on to the last talk of the session. Thanks, Professor.
Okay.
Is everything fine, Francisco? Can you also change your slides?
Yes.
Okay, are you ready?
Yes, thank you.
Okay, so the last speaker of this session is Francisco Mele, and he will be talking about restoring quantum communication efficiency over high loss optical fibers. Please.
Okay. Okay, thank you. This is a joint work with Ludovico Lami and Vittorio Giovannetti. And the goal of this talk is to understand how to reliably transmit qubits across long optical fibers. The problem is that until today, optical fibers have not been able to transmit qubits over long distances. This impossibility comes not only from technological limitations, but also from more profound theoretical reasons. However, these theoretical reasons rest on assumption, the so-called memoryless noise assumption. Under this assumption, the noise which affects the signals traveling across the optical fibers, this noise acts identically and independently on each signal. In other words, under this assumption, the noise is statistically the same. However, it has been experimentally verified that this assumption is not always true. In particular, it is false when the signals are separated by a sufficiently short time interval. In this case, memory effects in the noise arise. There is a possible known solution to the problem of transmitting qubit across long optical fibers, which is the solution of exploiting quantum repeaters every few tens of kilometers along the optical fiber. However, this solution is expensive. Our solution does not need quantum repeaters. Instead, our solution exploits memory effects in optical fibers. The basic idea is that the noise can be influenced by the signals sent before. We derive two main results. The first main result is that by properly taking into account the memory effects in our model, unassisted quantum communication is possible at a fixed qubit rate for all non-zero values for the transmissivity of the fiber. And the transmissivity of an optical fiber is typically exponentially decreasing in the length of the fiber. And this fixed qubit rate is independent of the transmissivity. Our second main result says that entanglement assistance and the proper memory effects exploitation allows one to completely neutralize the effect of noise in classical communication. The scenario of quantum communication theory is the following. Alice wishes to send information to Bob across a noisy communication line. The noise is mathematically characterized by a quantum channel, which is a suitable map between the space of density operator of the signals that Alice sends in the channel and the space of density operator of the signals that Bob receives. Across a quantum channel, it is possible to transmit different types of information, qubits or bits. And for each of these possibilities, there is a notion of capacity of the quantum channel phi, which measures the usefulness of the channel to transmit the type of information desired. If the goal is to transmit qubits, one defines the so-called quantum capacity as the maximum over all the possible strategies of encoding and decoding of the so-called qubit rate, which is the ratio between the number of qubits transmitted with zero error and the number of uses with the channel. Analogously, if the goal is to transmit bit, one can define the classical capacity. If Alice and Bob can exploit pressured entangled states in their encoding and decoding strategies, one defines the entanglement assisted capacities. And in these figures, I have implicitly assumed the memoryless noise assumption. Indeed, I have the noise as represented by the same quantum channel phi. Now let us talk about the communication scenario we deal with in our works. The quantum information carrier, the signal, is a single mode of electromagnetic radiation with definite frequency and polarization. This system is associated with the Hilbert space of a quantum harmonic oscillator. Now let us define the quantum channel. To do so, we first define an environment, which is a single mode like the system, and we fix two parameters. A parameter lambda, which is a number in 0, 1, and an environment state, sigma. A general alternator phi of lambda sigma is a quantum channel which is defined by its action on the input state in this way, where U of lambda is the beam splitter unitary, where A and B are the annihilation operators of the system and of the environment respectively. The beam splitter is a semi-reflective mirror. The general alternator phi of lambda sigma acts on the input state rho by mixing it with an environment state initialized in sigma through a beam splitter of transmissivity lambda. And the output at this arm of the beam splitter is the output of the general alternator. And roughly speaking, lambda represents the fraction of the input state which is transmitted from the input to the output. For example, if lambda is equal to 1, if lambda is equal to 0, then the channel is completely noisy. And hence the capacities are always 0 if lambda is equal to 0. And if lambda is equal to 1, is that the channel is noiseless. In other words, the channel is equal to the identity map. Since in practice, Alice can produce only those input signals which satisfy an energy constraint, since in the laboratory we have a finite energy budget. In this scenario, one talks about energy constraint capacities, which are defined as the previous capacities, but the strategies, the encoded strategies are restricted only those strategies which whose input signals have satisfy an energy constraint, where N capital denotes the energy budget available in lab. Now, let us talk about optical fibers. In the best studied model of optical quantum communication, optical fibers are represented by thermal attenuators. Thermal attenuators are a particular family of general attenuator where the environment state sigma is a thermal state. And it turns out that the quantum capacity of the thermal attenuator vanishes if the transmissivity is lower than 1/2. This means that sufficiently long optical fibers cannot transmit qubits with 0 error. However, in this paper, a phenomenon dubbed Dayard quantum communication has been shown. And this theorem says that for all values of the transmissivity, there exists a suitable environment state such that the quantum capacity of the corresponding general attenuator is larger than a positive constant. And this result holds even if we put an energy constraint at the input of the channel. In words, this result means that by choosing the environment state, by manipulating the environment state, quantum communication across this general attenuator is possible even if the transmissivity is very low, non-zero, but very low. And now let us talk about our results. Overwhelming numerical evidence suggests the validity of this conjecture, conjecture 1, which can be regarded as an entanglement-assisted version of the effect of Dayard quantum communication. The conjecture says that for all values of the transmissivity and for all values of the energy constraint, there exists a suitable environmental Fock state such that the energy constraint entanglement-assisted classical capacity of the corresponding general attenuator is larger than the classical capacity of the noiseless channel. And this conjecture is not a conjecture in the seemingly worst case when the transmissivity tends to 0, because we have a proof of it. And in words, this result means that by consuming pressured entanglement and by controlling the environment state, it is possible to communicate with the same or even better performance than the unassisted case of absence of noise. And in order to show this result for sufficiently small transmissivity, non-zero values of the transmissivity, we have introduced a novel method to easily deal with the calculations involving thermal attenuator. The thermal attenuators are really important in literature because are the standard model to describe optical fibers. However, calculating the output of the thermal attenuator is often cumbersome. For example, if one needs to compute the von Neumann entropy of the output of a thermal attenuator, if the input is a Gaussian state, then the calculation of the entropy is easy. However, if one needs to compute the von Neumann entropy of the thermal attenuator applied to a non-Gaussian state, then the calculation is difficult. And we overcome this problem by introducing a trick that we dubbed master equation trick. And we derive a simple cross representation of the thermal attenuator, exploiting the associated Lindblad master equation. And this allows us to obtain simple expression for the output of the thermal attenuator and for the evaluation of the entropy for particular non-Gaussian states. And this result, this trick can be generalized also to other fundamental Gaussian channels, such as the thermal amplifier and the additive Gaussian noise. Now, the Dayard quantum communication phenomena and its entanglement assist version established that the control of the environment state guarantees very good communication performances. So in order to give a technological value to these results, we need to reply to this question: how to implement in a realistic way the control of the environment state? We reply to this question by exploiting memory effects in optical fibers. Memory effects in quantum communication theory can be described by the model introduced in this paper. The model is the following. The channel environment the environment is split in two parts. A local part E, which is the single mode environment which we have considered so far, and also a huge reservoir, a remote part of the environment. This huge reservoir R induces a thermalization process onto the environment, and this thermalization process tries to reset the environment into the initial thermal state. And at the same time, the environment, the local environment, the environment is altered by the signals sent by Alice through the beam splitter unitary. And so we have this collisional model. And the thermalization process is characterized by a one-parameter family of quantum channel, where the parameter is a time interval delta t. And this quantum channel satisfies the following conditions: that if the time interval is larger than a certain thermalization time t with t, then the quantum channel resets the environment into the initial thermal state. And if the time interval is very, very small, then this quantum channel acts like the identity map. And in the paper, we formalize this condition by using the energy constrained diamond norm between this quantum channel and the identity map. And so I want to remark that this model reduces to the thermal attenuator model in a particular case. Indeed, if the time interval delta t between signals sent by Alice is sufficiently large, then the environment has enough time to reset into the initial thermal state between subsequent signals. And so when a signal interacts with the environment, the signal sees the environment initialized into the thermal state. And so the input-output relation is implemented by the thermal attenuator channel description. And so the memoryless noise assumption is recovered. In the opposite regime, when the time interval delta t is sufficiently short, then the environment has not enough time to reset into the initial thermal state. And so when a signal interacts with the environment, then it does not see the thermal state, but it sees an environment which is in a state which depends on the signals that Alice has sent before. In other words, there are memory effects. And in this regime, Alice can exert a certain level of control onto the environment state. Let us put this idea together to devise a protocol that we dubbed noise attenuation protocol. The protocol is the following. Step 1, Alice waits for a thermalization time so that the environment can reset into the initial thermal state. And the goal of the protocol is to obtain a general attenuator phi of lambda sigma, which is less noisy than the initial thermal attenuator. And so the step one, Alice only waits for a thermalization time so that the environment can reset into the initial thermal state. Then, at step 2, Alice sends k signals, dubbed trigger signals, separated by a time interval delta t, initialized in a suitable state. And these k trigger signals do not encode information, but are only sent to alter the environment in a suitable way. And step 3, after a time delta t, Alice sends an information carrying signal, which interacts with the environment altered in a suitable state sigma. And then she goes back to the step 1 unless the communication is complete. And we only consider those environment states sigma, which can be achieved by the noise attenuation protocol. In other words, we consider only those environment states sigma, which can be obtained as the environment output by sending trigger signals. If rho k is the state of trigger signals, then after the interaction between each of these k trigger signals with the environment initialized in the thermal state, then the environment can be written in this form, where U is the beam splitter unitary, which couples the signal and the environment. And then we have to take into account also the thermalization process which acts on the environment. Delta T, since the time interval between subsequent signal is delta T. And we need to choose rho k carefully in order to achieve an environment that which guarantees good communication performances. And we prove this theorem that if Alice sends sufficiently large number k of trigger signals separated by a sufficiently short time interval, initialized in a suitable state, then the environment is altered in a state sigma, which satisfies the phenomenon of diode quantum communication. That is that the quantum capacity of the corresponding general attenuator is larger than a positive constant, even if we put an energy constraint at the input of the channel. And this state of trigger signals can be produced by using linear optics and Fock states. And what I mean that this state sigma can be written in this form for a suitable choice of rho k and delta t sufficiently short. Now, there is a drawback in the previous construction, since we need to take into account also the trigger signals in the evaluation of the rate of the protocol. And the maximum rate achievable by adopting the noise attenuation protocol with k trigger signals sent to alter the environment into sigma is the ratio between the quantum capacity of the general attenuator obtained at step 3 and k plus 1, where k is the number of trigger signals. And the previous theorem may require K to be large. And if K is large, this ratio is low. Fortunately, we show that just K equal 2 is enough to activate the phenomena of diode quantum communication if the transmissivity is non-zero but sufficiently small. We prove this result. It can be regarded as a cheaper version of the previous theorem. Suppose that the transmissivity is non-zero but sufficiently small, and suppose that Alice sends 2 trigger signals separated by a sufficiently short time interval delta t, initialized in this state of 2 trigger signals. Then the environment is altered into a state sigma, such that the phenomenon of diode quantum communication holds. That is, that the quantum communication of the general altimeter, the corresponding general altimeter, is larger than a positive constant. And we have generalized these results to the entanglement assisted scenario. And the result is that if conjecture 1 is true, then the noise attenuation protocol allows one to activate the entanglement assisted version of the phenomenon of diode quantum communication. That is that the noise attenuation protocol allows one to alter the environment in an environment state sigma, such that the energy constrained entanglement assisted classical capacity of the corresponding general altimeter is larger than the classical capacity of the noiseless channel. And by exploiting memory effects, which can be described by the model we have presented, we can activate this phenomenon of diode quantum communication to enhance the performance, to improve the performance of communication. And the take-home message of this talk is that memory effects are not bad. Instead, memory effects can be engineered to improve the communication performance. And in the model we have introduced, the noise attenuation protocol allows arbitrarily long optical fibers to reliably transmit qubits at a fixed positive rate and bits and qubits at the maximum achievable rate in the noiseless scenario, provided that pressured entanglement is consumed. Thank you for the attention.
Thanks a lot, Francisco, for this very nice talk. We have enough time for a few questions. So perhaps I have a naive one. So you have this interval delta t, right? It's to ensure that you have this memory effects. Do you have any quantitative bounds on how small this delta t has to be, or is there a way to quantify this?
We have not a quantitative bound on how short has to be this time interval, but we are establishing collaboration with experimentalists to try to estimate this thermalization time below which these memory effects arises. But we can try to use we can have a rough estimate by reading the usual repetition rate that are used in the nowadays quantum communication platform, which I think that they use a repetition rate of the order of 1 gigahertz. So I think that this time interval has to be less than 1 nanoseconds.
Okay.
And but we are trying to establish an experimental collaboration too.
Okay, sounds good.
Thank you.
Do you have any other question? Okay, then if not, let's thank Francisco once again. Thank you very much.
Thank you.
Okay, so this is the end of the session. See you tomorrow.
See you tomorrow.